Hello friends, I am Vidya Patil, Assistant Professor, Department of Mechanical Engineering in Sharad Institute of Technology, Polytechnic, Yadra. Today we are going to continue our fifth unit of Refrigeration and Air Conditioning for the subject Power Engineering and Refrigeration. In this session, we are going to cover the problems related to Carnot cycle and calculation of the coefficient of performance in refrigeration air conditioning chapter. First I read problem number 1, that is, an inventor claims to have developed a refrigeration unit which maintains the refrigerated space at -6 degrees centigrade while operating in a room where the temperature is 27 degrees centigrade and coefficient of performance, that is COP, is equal to 8.5. So we have to find out whether his claim is correct or not. Okay, first one thing, I want to clear that when the any machine have the coefficient of performance more than the coefficient of performance of Carnot refrigerating operating between same temperature limits, okay, that is we have to check to whether his claim is correct or not. Okay, and for that purpose we have to calculate the Carnot refrigerator per Carnot refrigerator COP. Okay, first in this problem, first we write down the given data. First, the temperature of source, that is T1, and the temperature of sink, that is T2. Okay, temperature of source, that is T1, is given here, that is room temperature 27 degrees centigrade. Okay, and the temperature of sink, that is T2, that is the refrigerated space temperature is given here, that is -6 degrees centigrade. So we can convert these both temperatures in Kelvin. Okay, so 27 plus 273 is equal to 300 Kelvin for T1, and -6 plus 273 is equal to 267 Kelvin for T2, that is temperature of sink. To check the claim is correct or not, first we have to calculate the maximum possible COP, coefficient of performance, of Carnot refrigerator, that is COP. Okay, Carnot refrigerator COP is equal to T2 divided by T1 minus T2. Okay, so T2 is given here 267 Kelvin, T1 is 300 Kelvin. So we put these both values in this formula, then we get the COP of refrigerator is equal to 8.09. Okay, so and here in this problem the COP is given 8.5. So no machine can have COP more than COP of Carnot refrigerator operating between same temperature limits. So this inventor's claim is not correct, because as his COP is 8.5 and our COP, calculating COP is refrigerator COP is 8.09. So there is some difference, that is 8.09 and 8.5. So the inventor's claim is not correct here. Now next we see next problem, that the inventor has claimed to have manufactured a refrigerator having COP 7.4 while working between -10 degrees centigrade and 30 degrees centigrade, and we have to again check here his claim is correct or not. Okay, first again we write down the given data from problem, that is temperature of source, that is T1, is equal to 30 degrees centigrade, and temperature of the sink, that is -10 degrees centigrade. So again we convert here both values of temperature in Kelvin, degree centigrade to Kelvin, by adding 273 here. So by T1 is equal to 303 Kelvin and T2 is equal to 263 Kelvin. So again here we calculate COP of Carnot refrigerator Okay, that is standard Carnot refrigerator value, and we compare our value from problem of COP for that COP in Carnot refrigerator. Okay, so we calculate COP of refrigerator by using formula T2 divided by T1 minus T2. So T2 is 263 and T1 is 303. So by putting these all values, we calculate COP of refrigerator is equal to 6.575. So again here the no machine can have COP more than COP of refrigerator. Here in problem COP is given 7.4, and in after calculating value is 6.57. So again inverter's claim is not correct here because the values are different, as COP 7.4 which is more than Carnot COP which is 6.575. So again inverter's claim is not correct. When inverter's claim is correct, when the COP value is less than the COP value of refrigerator, that time only inverter's claim is correct. Okay, both are same example, 1 and 2 are both are same examples here. Okay, now we see next example. Here the Carnot refrigerator requires 1.25 kilowatt per ton of refrigeration to maintain the temperature of 243 Kelvin. Okay, so we have to find here the COP of Carnot refrigerator and second temperature at which heat is rejected. Okay, first we understand the Carnot cycle. Okay, here the Carnot cycle is shown here. Okay, the PV and TS diagrams are shown here. Here process 1 to 2 is reversible isothermal heat absorption process. Okay, at lower temperature T2 from body to be cooled, and 2 to 3 is reversible adiabatic compression to higher temperature T1. So again 3 to 4 is reversible isothermal heat rejection process at higher temperature T1, and 4 to 1 is reversible adiabatic expansion process to lower temperature T2. Okay, so here QR is the heat rejected and QA is the heat absorbed from the body to be cooled. Okay, so again here we have to calculate the COP of Carnot refrigerator and temperature of which heat is rejected. So for that first we see the compressor work which is given here 1.25 kilowatt, and refrigerating effect is given, that is 1 ton for the 1 ton. So 1 ton is equal to 3.517 kilowatt. Okay, so before that first we calculate COP of Carnot refrigerator. Okay, for that here the formula is used, refrigerating effect divided by compressed work. Okay, because last problem we use formula T2 upon T1 minus T2 here, but here the temperature at which heat is rejected is not given here, that we have to calculate here. That's why we use this formula here. COP of refrigerant is equal to RE, that is refrigerating effect, divided by compressed work. So refrigerating effect is 3.517 kilowatt and compressed work is 1.25. So here COP of refrigerant is equal to 2.8. Again now here we calculate COP of Carnot refrigerator. Now we have to calculate the temperature at which heat is rejected. So for that purpose we use formula COP of refrigerant is equal to T2 divided by T1 minus T2. Here the COP of refrigerant we just calculate as 2.8 and T2 is 243, and again we put the values of T2 here, and here we calculate the value of T1 is equal to 330 Kelvin, that is temperature at which heat is rejected, that is T1. Here in TS diagram also we can see at T1 to 2 there is heat is absorbed, and 3 to 4 again there is heat is rejected. So T1 and T2, at T1 heat is rejected and at T2 heat is absorbed. So we have to calculate here T1. Okay, so this is the calculation of COP of Carnot refrigerator and temperature at which heat is rejected. Okay, now we see next problem, that is here in this problem 1.5 kilowatt per ton of refrigeration is required to maintain the temperature of minus 40 degrees centigrade in the refrigeration cycle which works on the Carnot cycle. And here we have to calculate COP of cycle, temperature of source and heat rejected per ton of refrigeration. Okay, again here the Carnot cycle is shown, PV and TS diagrams are drawn here. We just discussed that 1 to 2 and 3 to 4, that is 1 to 2 is heat addition or heat absorb, and 3 to 4 that is heat rejection. Okay, and again in TS diagrams we can see here there is a 1 to 2, again in TS diagram there is a heat absorb, and 3 to 4 there is a heat rejection. Okay, we already know the process 1 and 2, and 1 to 2 is reversible isothermal heat absorption process at lower temperature, and 2 to 3 is reversible adiabatic compression at higher temperature. 3 to 4 is again reversible isothermal heat rejection process at higher temperature, and 4 to 1 is reversible adiabatic expansion at lower temperature. Okay, so here again we have to calculate COP of cycle, and for that purpose we first calculate compressor work, that is already given 1.5 kilowatt for 1 ton refrigeration effect, that is 3.517 kilowatt, and we calculate COP of Carnot refrigerator by using formula refrigeration effect divided by compressor work. So here refrigeration effect is 3.517 divided by compressor work is 1.5. So COP of refrigerator is equal to 2.345. Okay, now here next we have to calculate the temperature of source. The temperature of source here, that is T1, and temperature of sink, that is T2. Okay, and they are given the temperature of sink, that is T2 is equal to minus 40 degrees centigrade. So we convert this value of degree centigrade into Kelvin by adding 273. So temperature of sink, that is T2 is equal to minus 40 plus 273 is equal to 233 Kelvin. So we have to calculate T1 here. Again in last, same as it is in last problem, we use a coefficient of performance for the refrigerator next by changing formula T2 upon T1 minus T2. So COP of refrigerator just calculated as 2.345 and T2 is 233, and we have to calculate T1. So T1 is equal to 332.36 Kelvin. So next we have to calculate the heat rejected per ton of refrigeration. Okay, so heat rejected, that is QR, and heat absorbed, that is QA. I just explained in Carnot cycle, heat is rejected in 3 to 4 and heat is absorbed and process 1 to 2. Okay, so heat is absorbed, that is refrigeration effect. Okay, just we have to calculate, that is RE is equal to 3.517 kilowatt. So we have to calculate the heat rejected. So you use coefficient of performance refrigeration formula, that is QA divided by QR minus QA. QA is the heat absorbed, QR is the heat rejected. So COP of refrigerant by putting all values, we just calculated COP of refrigerant, that is 2.345, and QA is the refrigeration effect, that is 3.517, and QR, by putting this value we calculate QR is equal to 5.017 kilowatt. Okay, so in this way three formulas are used for the coefficient of refrigerator here. First is refrigeration effect divided by compressor work. Second is T2 divided by T1 minus T2, and third is the QA divided by QR minus QA. So we have to remember these all formulas, how to use in which situation and which terms we have to calculate that time. Okay, in this way we can see the next problems also in next session. Okay, thank you.